So, my name is Benjamin Junkins. I'm a math student here, and today my presentation is on expanding the quadrature of the parabola to cubics. Now, what the quadrature of the parabola is it's a letter that Archimedes wrote to one of his friends describing how the area of a bounded parabola can be related to the ratio of a triangle inscribed in that parabola. Now, in order to get to cubics, we're going to need the help from a little guy named Francois Viet. Now, Viet was many things. He was an attorney, a private counselor to Henry III and IV, and he was actually a well-known figure in mathematics at the time, but wasn't really recognized for the work they put into math. One of his more notable things is representing an infinite product as a formal equation. He was the first person in history of math to do this. In fact, that was the first infinite product representation of pi that we have known to this date. Now, what's important that we're going to use are his formulas. Vieta's formulas, long story short, represent the relationship between coefficients of a polynomial and the roots of a polynomial. Now, the roots are where the polynomial hits the x-axis, you probably know. But the way you derive his formulas is you basically factor out the polynomial, distribute it out, and then you set the coefficients equal to the roots right here. So, for example, if you have the second root, or the second coefficient in a polynomial, it's going to be the sum of the roots. So what we're going to use is a cubic polynomial, ax cubed equals bx. We're going to call that a depressed cubic polynomial. And notice with Vieta's formulas, the second coefficient is missing. That means that second coefficient is going to be equal to 0. So by Vieta's formulas, the sum of the roots of this depressed cubic formula are going to be equal to 0. The way that's useful is we can now set a cubic or a depressed cubic equation equal to, say, a line, mx plus n. We can set all that equal to 0, move it all to the left-hand side, and then using Vieta's formulas, we still see that the roots of this equation right here are going to be equal to 0. And those roots are going to be where this line intersects the cubic polynomial. So, we just have a simple one-function calculator. Say you have roots -3, -1, then your fourth root is going to be 4. So a few examples of this. Archimedes, simple corollary from Archimedes' quadrature of the parabola is that you actually get a nice closed formula for a bounded area of a parabola right here. It's going to say you have a quadratic function ax cubed or ax squared, then you're going to have the leading coefficient times the difference of the roots cubed over 6. And then you also, if you expand that to a depressed cubic, you get another similar formula popping out using Vieta's formulas and a little bit of calculus to derive this one. You get the leading coefficient times the difference of the roots raised to the 4th power over 12. And this is really convenient if you want to memorize these formulas other than using calculus, because now we have just simple closed formulas instead of having to go through integrals and all that. Now, going back to the quadrature of the parabola. So what it says specifically is that if you have this blue triangle right here, then that blue triangle is going to be 4/3 the total area of this parabola right here. Now this goes into the derivation and the specifics of the quadrature of the parabola and what Archimedes did, but the main point to take away from this is that Archimedes found that every subsequent triangle that you make is always the sum of those new areas is always going to be 1/4 the previous area. So you have an infinite sum popping out right here. And Archimedes knew at the time that this infinite sum converged to 4/3. So you always have 4/3 x, where x is the area of this blue triangle. And the area of x can be derived using simple analytic geometry, but we won't get too much into that. So remember that the area of a bounded triangle is 4/3 the area of the inscribed triangle. So what we use is we use Vieta's formulas to find that going through a lot of complex math that I won't get too much into, is we found that the area of bounded cubit is 9/8 the area of the inscribed triangle. Now with this inscribed triangle, a few things you have to note is that it has to be symmetric. So whatever point you use tangent to the cubic right here, it has to be symmetric about the origin, just so you have these areas canceling out right here. And using Vieta's formulas, we can find that this area is indeed 9/8. Now, pattern pops out. With quadratic, you have y equals ax squared, so the area, the ratio of the triangle and the area is 4/3. With cubic, you have 9/8, for that being the ratio, which is 3 squared over 3 squared minus 1. So we have 2 squared over 2 squared minus 1, and 3 squared, 3 squared minus 1. And then we actually found for quartic also, which is incredibly hard to do, it's orders of magnitude harder, is 4 squared over 4 squared minus 1. So a neat little pattern pops out that we weren't able to prove in general, but we definitely conjecture that it could be proven up to any nth degree polynomial. Now, to take away from this is Vieta's formulas relate a good deal with polynomials that we aren't taught in math classes in high school. For example, these little tips and tricks that you can use. Basically, there's something that we should look at for future educational purposes. Vieta's formulas can be applied to a variety of problem solving polynomials, finding the bounded area, as we saw for calculus classes, and infinite sums, intersecting the depressed cubics, etc. So you can use these as Vieta's formulas in a variety of different ways, a variety of different problem solving techniques. And they are definitely need a better place in math. And that is my presentation. I guess that's that. Yes, questions? Yes.
What kind of projects would this formula be applied to?
Vieta's formulas, so Vieta's formulas, it's various formulas, and any project involving polynomials. If you have anything to deal with polynomials, you can take Vieta's formulas and go crazy with it, especially if you're trying to find roots of polynomials, because if you know what Vieta's formulas state, is if you know coefficients of polynomial, you basically know some information about roots, and vice versa. Yes?
Do you think there's a way to combine the geometry and the algebra of it too? Because people tend to think of those as two separate things.
Yes. So it's very good for, I've found, especially in going up to the quartic case, analytic geometry, just finding a connection with that, it definitely has potential to bridge that gap. Yes. Any other questions?
Thank you.